start with the same way we started with the respiratory system. 6 functions of the urinary system. The number one thing that you learned in chapter 1 when we went big picture over all the different systems of the body. Yeah, more specifically, what do the kidneys do? Filter the blood for what reason?
It's a little.
To remove.
Stop complaining. At least I did it.
Metabolic waste products. Metabolic waste, which will become toxic. And while they're at it, since we have to reabsorb 99% of the filtrate, we're going to bring what into homeostasis? Fluid and electrolyte. So fluid and electrolyte balance. And just like the lungs, they can help with pH balance by, if I'm too acidic, excrete hydrogen ions, and if I'm too alkaline, excrete a bicarbonate. And since I've got 25% of my blood flow going through the kidneys, I put a couple of chemoreceptors in there that sense oxygen. And what could my kidneys do in response to hypoxia? Yes, red blood cell production by secreting erythropoietin and triggering erythropoiesis in the red bone marrow. And what else can the kidneys do? Blood volume by activating the renin-angiotensin feedback loop. And the last one is called other metabolic functions, and that includes 3 things. They will help my liver with detoxification, and they put the finishing touches on something that was started by vitamin D. Starts in the skin, wraps up in the kidneys. Who would have thunk?
Not me.
And in the case that I'm starving, they will also help the liver with making glucose in a process called
Gluconeogenesis.
Gluconeogenesis. There you go. All right, there's that start. Now on to the kidneys. Okay, you have 2 main, what's your functional unit of the kidneys?
Nephron.
Nephron. What are the 2 main parts of a nephron? Okay, I'll give you half credit for that first answer. Glomerulus is part of a bigger structure.
Renal corpuscle.
Renal corpuscle. So you have the renal corpuscle and then you have the tubules. What process happens in the, okay, let's even back off even further. We have 3 main processes which happen in your nephrons. What are the 3 main processes? Filtration, reabsorption, and secretion. Okay, where does filtration occur? That's in your renal corpuscle. And the renal corpuscle has the filtration membrane in it. What are the components of the filtration membrane? Yep, fenestrated capillaries, basal lamina, and podocytes. So, how is this set up, basically? If you thought of that as a series of sieves. Okay, so which one is designed to keep the biggest stuff out? Fenestrated capillaries. And what stuff does that effectively keep out of the filtrate?
Proteins.
Platelets, red blood cells, and
Proteins.
white blood cells.
Oh.
Then we go to your basal lamina, which is basically a fusion of the fenestrated capillaries and the podocytes. And then when we get to the podocytes, what are the podocytes keeping out of the filtrate?
Proteins.
That's where we're going to keep out the proteins, such as albumin, because it goes like big, middle size, and then small. Just think of this as like a mesh network of collagen fibers. And just like filtering it through your coffee filter or something like that. All right, so that is your filtration membrane. And we have, wow, where did that go there? Where does it talk about? Oh, that's my review. That's why I'm like, we're not there yet. We have, when we talk about filtration, what is
Me?
our normal GFR?
I thought you were getting this one. Like, you don't really smell it.
Normal, okay. Normal GFR. Glomerular filtration rate. You're talking about the pressures. 125 milliliters per minute. Yeah, per minute. And so anything that alters three forces, we have three forces at work in the glomerulus. What are those three forces at work? What is that? I didn't hear that. Glomerular hydrostatic pressure. And is this a positive or a negative force?
Positive.
Positive force causing fluids and solutes to come through.
Something
What's our next one?
Yeah. Yeah.
Colloid osmotic pressure. And is this positive or negative force?
Negative.
Negative. It's going to push stuff back into the glomerulus. And our last one is
Capsular hydrostatic.
capsular hydrostatic pressure. And is that positive or negative? That is also negative. When you look at the numbers, it is 50, 30, and 10, I believe. So now your net filtration pressure is 10. All right. So anything that either alters your colloid osmotic pressure, changes the number of particles in your blood, or messes with your blood pressure is going to wreak havoc in the kidneys. What would be the consequences if my blood pressure got way too high? Okay, we're going to blow up the nephrons, blow out the glomerular membrane, and my filtration rate could be so high that can't what? Remember what happens as you go through the tubules? What are we going to do to
The little
99%?
liquors won't catch it.
Reabsorption. You're not going to do a good job of reabsorption because that filtrate is going to whip through those tubules so fast you're not going to be able to reabsorb all those valuable nutrients. And what would be the concentration? What would be the consequences if my filtration or my blood pressure got too low?
It would filter too much. And the little lickies would catch it.
Wouldn't filter enough, and I could become toxic because it's not filtering fast enough to remove the toxins. All right, so there's our three. And how much filtrate do we create in our two kidneys every day? 180 liters, yes. Now, since maintaining blood pressure going through the renal corpuscle is so important, we have a couple of different measures to make sure that we have constant blood pressure and a constant net filtration rate. We have a process called auto-regulation, where the kidneys just take control of it themselves and do it all by themselves. It doesn't have anything to do with your nervous system. What is the first method of auto-regulation that has to do with muscle? Yeah, what's the name of it? We want the name. The myogenic mechanism. And in a nutshell, how does the myogenic mechanism work if my blood pressure is too high? So if my blood pressure is too high, it does what to my GFR? It's going to increase my GFR and get way too high. So how am I going to bring that back to normal? Going to constrict the afferent arterial. And when I constrict the afferent arterioles, what does it do to the blood flow coming into the glomerulus? Decreases it and brings my filtration rate back to normal. And if my blood pressure is too low, what will it do? Vasodilate, make the diameter bigger, increasing blood flow in an effort to get back to normal net filtration pressure. The second one is called tubuloglomerular feedback. Okay, now for this one, I'm going to bring the picture up to help your explanation. What happens in this tubuloglomerular feedback mechanism if my blood pressure is too high? So the macula densa cells sense that the salt content in the filtrate is too high. We have not had enough time to reabsorb the salt. So in response to that, your macula densa cells are going to they're going to tell the JG cells to secrete vasoconstricting chemicals, which will then cause the afferent arteriole to constrict, reducing blood flow into the glomerulus. If your macula densa cells taste too little salt, your filtration rate is? If they taste too little salt,
it's too slow.
It's too slow. They've had so much time to reabsorb that salt. So, how will they speed up the filtration rate if it's too slow? They're going to, the macula densa cells are going to tell the JG cells
To stop.
stop secreting your vasoconstricting chemicals, which will allow the afferent arteriole to vasodilate and speed up the rate of filtration. Does that make sense?
Yes.
You were a little sketchy on that, but I hope after going through it, it rang a bell.
Yes.
Okay. Flip it.
Yeah, I'm good now. But
All
that
right.
was also the lecture I missed. So.
Okay, now, if auto-regulation doesn't work, then we're gonna kick in hormonal regulation of GFR, and that has to do with renin, aldosterone, angiotensin feedback loop. So in that case, what is going to be the stimulus to kick this in? Low blood pressure, which corresponds exactly with low GFR, low glomerular filtration rate. And in response to that, the JG cells will secrete what chemical? Renin, which is an enzyme which converts angiotensinogen, a blood protein, to angiotensin 1, which goes to the where it finds ACE, angiotensin converting enzyme, which converts angiotensin 1 into
Angiotensin 2.
which has 5 impacts on the human body to help bring back normal filtration. The first 2 are temporary. What will angiotensin 2 do to temporarily make sure the kidneys are able to filter toxins out of the blood? Yes. Vasoconstrict the efferent arteriole, which is basically reducing the diameter of the drain. So if you plug up the drain, you still got it coming in the faucet, that's going to increase your filtration rate just so that you can get the toxins out. And another temporary thing is to vasoconstrict what? Yes, your systemic arteries.
Yeah.
And where does that push the blood to? Your core. It's your aorta, because it's the renal arteries which are going to be feeding your kidneys. Then we have 3 more mechanisms, and it really helps me when I think about these. What's our end goal of these last 3 mechanisms? We have to fix the real problem. What's the real problem here? Low blood volume. Low blood pressure caused by low blood volume. So that's what we're trying to fix. And if you can think of in your head, what can your body do to fix low blood volume? Think about hormones. What am I going to secrete? Aldosterone, which is going to trigger The reabsorption of
Sodium.
sodium, and I'm also going to secrete ADH, which is going to cause the reabsorption of water. And you know there's that little relationship there between water and salt. It's going to follow it into the body. And then we're going to do what in hypothalamus? Yeah, turn on the thirst center. So that we are going to absorb, we're going to drink more water, which will then assist this. And these three here will definitely help with the production of more blood volume. Now I have heard, just on the offsay, red blood cells are also a particle in the blood. So creating more red blood cells through erythropoiesis could be another method of helping to draw more fluids in. But this textbook does not talk about it, so we're not going to talk about that one. But I have heard that before.
I was thinking, oh, more particles in the blood.
And I've heard it. This textbook didn't talk about it, and it's like, I would think that that would be a way secondary way of doing it. This is much more direct. It's like, let's just get more fluids in there. Okay, so this is if low blood pressure is our issue. What if high blood pressure is our issue? What hormone are we going to secrete? Atrial natriuretic peptide, and how will that help fix high blood pressure? Excrete sodium. What follows sodium?
Water.
What does that do to urine volume? What does that do to blood volume?
Decrease.
You guys are getting that? Yes. All right, and okay, let's do some numbers. So this is still all about regulating GFR. Oh my God, can you imagine how much of this was dedicated to maintaining proper blood pressure and blood volume and GFR? Okay, so we had 125 milliliters per minute as our normal GFR. What is your definition of CKD? Chronic kidney disease. Less than or equal to 64
For 3 months.
3 months. And then what is renal failure?
Lower than 15.
Lower than 10, isn't it?
Yeah, I think it's less than 15 mils per minute is renal failure. And what are we going to do if our patient is in renal failure? Dialysis. If it's minor, we can do it at home. We're going to do what? Peritoneal dialysis. And if it is major, that we can't do it at home, we're going to do it at a blood center. Hemodialysis. If we get to this point of CKD and toxins begin to build up in the blood, that condition of excess toxins in the blood is called? Nope, sepsis is called when you have a bacterial infection. That could be a result of it, but there's actually a term, starts with a U. Uremia. That is the condition created when toxins start to build up and you're about, I put it with CKD because the definition is when your filtration rate is about half of normal, and this is pretty doggone close to half of normal. So this is about the point where you're going to start accumulating excess toxins, is at CKD. All right, now, sometimes we can try to treat high blood pressure by messing with this. How would that work? They gave you 3 examples of medications that could target different parts of the renin, angiotensin, aldosterone feedback loop. How would that help with high blood pressure?
Slow it down where you don't reabsorb so much water.
Yep, or another target?
Or sodium.
Sodium. We could do it either way. We could shut down the ADH. We could shut down reabsorption of sodium in the proximal tubules. We could shut down absorption of sodium in the distal tubules. Any of those whenever. Or we could block the conversion of angiotensin 1 to angiotensin 2 in the lungs. So anything that interferes with the renin-angiotensin feedback loop is always going to be done for one thing, to target high blood pressure. Okay? The reason I point this out is because later on we talk about another group of medications which are called diuretics. Diuretics are also known as water pills. Why would we put somebody on a water pill?
To decrease their water or volume
Okay, and what reasons?
or
High blood
edema.
pressure.
So they could also be used to treat high blood pressure, or a second reason for diuretics would be edema. So like when people are in congestive heart failure and starting to accumulate fluids in their legs, you don't usually use these for edema, but you would use diuretics for edema, because this would then carry over into type 2 diabetes and that kind of stuff. So you would be more prone to use a diuretic. You can use it for high blood pressure, but I just want to make you aware of the fact that you would also use it for treating edema in the body. Make sense? Okay. Okay. Yeah. Okay. Here we are in the proximal tubules of the kidney. What happens in the proximal tubules? We just finally finished glomerular filtration. Oh my God, that took forever. And now we're into the tubules. Yeah, isn't that a complicated process? Damn. Okay, so what was it that I wanted you guys to remember about reabsorption in proximal tubules?
90% of the reabsorption is not there.
Not much. Not much. No.
70%.
60.
65% of the reabsorption of the water and electrolytes, and 100% of the glucose, amino acids, and vitamins. So 65 and 100, depending on what you're talking about. So by far, this is going to be the majority of the reabsorption. What processes are used to drive reabsorption?
Concentration.
Okay, so where does it start? It starts with, what do we call this?
Sodium potassium.
Chapter 3, primary active transport. And then we will also create that concentration gradient so we can do secondary active transport. And then we're going to create concentration gradients for a type of passive transport called
Oh.
facilitated transport, driven by high concentrations of glucose here, low concentrations of glucose there. And then we're going to add to that the movement of water driven by a concentration gradient, which is osmosis. So what method of reabsorption is not used in your proximal tubules?
Co-transport.
We got co-transport. Whoops. Here's primary active, here's secondary active, here's passive transport, and here's passive transport. So what's not used in proximal tubules for reabsorption? None of them. They're all used. The co-transporter?
Yeah.
Okay, so what happens is with this sodium-potassium pump, we always pump 3 sodiums out, 2 potassiums in. We ignore the potassium because we put leak channels in there and potassiums just say equal. So because of this sodium transport, we keep sodium levels really low in here. Out here in the filtrate, we have high sodium levels. So this is the concentration gradient that we're going to use. Concentration gradient is a form of energy that we can tap into because these sodiums want to come in. So we put up a co-transporter. A co-transporter always brings 2 things at once. One of them has to provide the energy by following its concentration gradient. That's what sodium does. Sodium is going to follow its concentration gradient in, and using that energy as it flows in, it's going to bring a buddy with it. So it can bring in glucose, or it could bring in an amino acid. It could even bring in a vitamin if it wanted to. And then as glucose starts to build up in here, glucose levels will get high. So then we use a facilitated transporter to use passive transport to get glucose over into your interstitial fluid. And as all kinds of molecules build up here in the interstitial fluid, all particles, then water will follow passively in a process called osmosis. So that is your proximal tubules. All right, so let's get rid of this. We did our glomerulus. And we got our proximal tubules, our descending nephron loop, our ascending nephron loop, and our distal tubules. So here we learned 65% plus of all filtrate. What happens in your descending nephron loop?
Water.
Reabsorption of water only. So that is 20% of the water. What happens in our ascending nephron loop? Salt, so 25% of our sodium and chloride. And I'm pretty sure that we have potassium pumps in there too. And then by the time we get there, if you look at the numbers, we're up to 85, 90% of everything. So we're almost finished. So what is our job here in the distal tubules? Hormonally driven. Reabsorption and secretion. So if I have low blood pressure, I am going to secrete what hormone which will have an impact on the distal tubules and collecting duct? Low blood pressure. ADH and?
AMP? No.
Aldosterone. Low blood pressure. Because what would aldosterone tell those distal tubules and collecting duct to do? Reabsorb more sodium. And what would the ADH do? Put aquaporins in so that the water could follow that sodium back into the body. And on the other hand, if I have high blood pressure, I'm going to secrete what hormone? Atrial natriuretic peptide, AMP. And what will it tell the distal tubules to do? Stop absorbing any sodium. Leave it in the filtrate. And then the other hormone, which has to do with water balance in the human body, which would influence all three of those, would be? Renin. Yeah, renin. So those are the four most important ones which regulate water. And now you guys kind of understand why. All right. All right, let's go out of here. Let's see if there's anything else. Oh, yes.
Yes.
Oh, yes.
Seems like a big one, guys.
Yes, it does.
This is the one that I struggle with every single group of students that comes through here because this is just like flat out physiology. Explain the physiological mechanisms of glycosuria and polyuria to me. When blood glucose levels exceed 180 milligrams per deciliter, the co-transporters meet their transport maximum. This leaves glucose in the filtrate. Glucose is a particle which attracts water. So glucose in the filtrate is glycosuria, and polyuria is water being attracted to those particles. Do you see how all those little components come together to explain from a physiological viewpoint glycosuria and polyuria? How do you feel about that? Why do you think I walked through that with you?
Probably a short answer question.
Just wondering if you all understood it now.
So isn't that why, like, back in the old days, they used to actually taste the pee to see if it had sugar in it?
That's how doctors decided if somebody was a diabetic or not. They would actually taste the urine of their patient if it tasted. I'm not lying.
They're not, it really.
We didn't have glucose test strips back then.
That's the only way to do it. That's the
Yeah.
only way to do it, and it's the best way
Yeah.
to do
Can I
it.
drink some of your urine?
Absolutely.
And that tastes sweet.
Hey, baby. And it's bacteria free. Well, I don't know at that point in time. If you're passing that much sugar, you might have a UTI too, so I don't know.
Might not be the safest thing to do.
Yeah. All right.
People die by the age of 30.
Okay, so there's your concept,
Yeah,
diuretics.
do it.
Okay, now, we had two types of nephrons in the human body. What are your Joe everyday nephrons that make 80% of all your nephrons? Those are cortical nephrons. And the other 20% are a specialized type of nephron called a juxtamedullary nephrons. And their special job was giving the kidneys the ability to
Make dilute
dilute or concentrated urine. What is the mechanism by which juxtamedullary nephrons create that opportunity? Counter current mechanism, which basically means that the two nephron loops are going in opposite directions and they complement each other as they go in opposite directions. And the end result of the counter current mechanism is that here in the renal medulla, this is a pyramid. What do we create in this renal pyramid? A concentration gradient, which goes from 300 to 1200. This is what gives the opportunity to either make concentrated or dilute urine. Because if you remember, in a juxtamedullary nephron, by the time that filtrate gets to the distal tubules, what is the osmolarity of the filtrate in the distal tubules of the juxtamedullary nephron? It's 100.
I thought it was 100 in there somewhere.
Milliosmolar. So the condition of that filtrate is hypotonic. And so, if I am well hydrated and I do not release ADH, what kind of urine am I going to form? Large volumes of dilute urine. If I am in a state of dehydration and I release ADH, then I am going to make small amounts of concentrated urine. And it's all because of that concentration gradient created by the juxtamedullary nephrons.
Are you wanting us to know those numbers?
No, I want you to know about the concentration gradient. As long as you understand the concentration gradient, you'll be fine. All right. That was so much easier than explaining it the first time. Oh, Lord. All right, so there's that, It's all hormones, Okay, that was just getting you ready for the lab, so we don't really need to cover that. What shouldn't you find in urine? Let's just cover that.
Glucose.
Proteins.
Lots of ketones.
Lots of ketones, glucose. You guys have any questions about what you shouldn't find in there? Doesn't that all make sense now?
Yes.
What you shouldn't find in there?
This is why little ketones are found in your.
Yeah, you can find little amounts of ketones when, so it depends upon the situation. When would it be okay to find small amounts of ketones? When you have tapped into your fat reserves and are using it in a normal way, such as you exercise and you burn through your carbohydrate reserves and you start tapping into your fat reserves. So just to reiterate the question, which was on your lab, if a diabetic had large amounts of ketones, why is this an indication of disease?
Because they're using their fat cells.
Primary source of energy, because what are they not able to use at all? Glucose. You can't get glucose into the cells to make ATP with the glucose, so they're going to have elevated levels of blood glucose, but they're still going to have tons of ketones. In a healthy person, that will not happen simultaneously. You're going to deplete your stores of glucose, and then you're going to have some ketones in there just because you're burning fat. A couple of you did mention you could burn proteins, and that is correct. Burning proteins as a source of energy will create ketones in the urine also. My massage therapist, I've told you about her before, she's a little bit out there. She's all about her keto diet. And as I got a massage yesterday, she's like, yeah, I got back from vacation, started on my keto diet again, and man, 5 days into it, I peed on that dipstick that says I'm in ketosis already. And she was all kinds of happy about it. And I'm like, okay, sweetie.
Like, that's not good.
Oh, that's great.
It's good in her brain and for releasing happy neurotransmitters. I'm not going to argue because I'll lose that one. Okay. The ureter.
She's Louise.
Oh, I'm not going to argue with her while she's doing deep tissue massage on me. You think I'm going to argue with her? Hell no.
Yeah.
It's
She might get
painful
even
enough
deeper
already. Damn. Okay. The ureters and urinary bladder are lined with what tissue? Transitional epithelia. What is the stimulus to urinate? Stretch of the bladder. That information is sent to the spinal cord. How does the spinal cord respond? Louder. Sends back a parasympathetic nerve motor impulse to relax the internal urethral sphincter made of smooth muscle. By that point in time, the information has made it to your brain, and hopefully at the correct time, you will send what kind of a motor command? Somatic motor command to the external sphincter made of skeletal muscle, allowing it to relax. And what do we call that reflex? They're not normal. They don't call it the urinary reflex. They get that stupid word. Micturition. Yeah. Why? Why do they have to make everything so hard?
We should
We're
change
gonna
it.
need to know that.
The reflex itself is the same as pooping, so
No, I mean the micturition. The name that
you'd have to be able to recognize it. You're not going to have to come up with it. But if you say micturition, hopefully you'll go, oh yeah, that's that stupid name for peeing.
How do you spell it?
How do you spell it?
MICTURITION, something like that. Micturition. MICTURITION.
Sorry,
Okay.
that's what I started to think. Whatever you said.
All right, here we go. Last chapter. Fluid and electrolyte.